Hi. So we were studying about p block elements, and we were discussing about the group 15 and group 16. So I have a question for you from group 15. So we have two compounds of nitrogen. One is called trimethylamine. This is called trimethylamine. And there is another compound which is called tricylylamine. Right. So the question is that do they have same structure? क्या इन दोनों का structure same है? This is the question 1 about these two compounds. Should this be the structure of the trimethylamine? Very similar to ammonia, right? Where nitrogen is sp3 hybridized and has a lone pair on it and bonded to each CH3 molecule, or I would say moiety, through a sigma bond, right? And I believe this should also be the same structure with tricylyl. And should have same hybridization. It seems like that, but it is not, right? So why is not the case? Let's understand that. So this is an exceptional case, which you should remember from the competitive exam point of view, because what different happens here in case of tricylylamine. Let's see. Just to understand that, let me explain the hybridization of the trimethylamine. So I have nitrogen, and its valence shell electronic configuration is 2s2 2p3. So in its valence shell, I have 2 electrons in S and 3 electrons in P, right? It will hybridize all 4 orbitals and will form sp3 hybridization, right? Out of 4 sp3 hybrid orbitals, it will use 3 sp3 orbitals to form sigma bonds. And one of the sp3 hybrid orbital will be containing a lone pair. This is what really happens in case of trimethylamine or ammonia or any such similar compound, like for example in Cl3. But what happens in tricylylamine? The nitrogen has same electronic configuration 2s2 2p3. Electron pair is there in 2s, and 3 electrons are available in 2p. This is the normal state of nitrogen, or ground state of nitrogen atom, right? Now what happens is that one of the electron from 2s excites and goes to 2p before hybridization. So in its hybridized state, the electronic configuration will be 2s and 2p4. I'll tell you why it does that. So it will use these 3 hybrid orbitals and will form sp2 hybridized orbital, or hybridization will be sp2. So now it has one lone pair of orbital which is not in hybrid orbital but available in normal atomic p orbital. Okay. So how does it have an advantage? Should I erase this part? The advantage of keeping this hybridization is that in sp2, nitrogen will be forming a trigonal planar geometry. It will be a linear molecule. So there will be 3 SiH3 bonded to it, and the whole system will be in one plane, right? Which will be the plane of the board. Now this nitrogen has a lone pair on it, which is in the p orbital. So for example, if this is x and y and this is z, and the plane of the board is xy plane. So when x and y are utilized in sp2 hybridization, then z is left, which will be perpendicular to the plane, right? So these 3 hybrid orbital will be in the xy plane, and pz will be containing a lone pair and will be present in the z axis, or in pz. Now silicon has, if I talk about silicon, silicon has some 3d orbitals which are vacant. Right? इसके पास 3d का orbital है जिसमें कोई भी electron नहीं है. So nitrogen has a lone pair and silicon has a vacant d orbital, so the two can form a pi bond. Similarly, this silicon has a vacant d orbital and the nitrogen has a lone pair, the two can form a pi bond. Similarly, this nitrogen has a lone pair and this silicon has a vacant d orbital and can form a pi bond. So this nitrogen's lone pair, which is present in p orbital, will be forming pi bonds with each of the silicon atoms, and it will be delocalization case. So they're forming p pi d pi bonds. Okay. So due to strong p pi d pi bonding which is happening between p orbital, specifically 2p orbital of nitrogen and 3d orbital of silicon, this takes up the geometry which is called sp2. So definitely the two doesn't have the same structure. So trimethylamine has tetrahedral geometry and trigonal planar shape. Oh, sorry, I'm so sorry. Tetrahedral geometry and trigonal pyramidal shape. And in case of tricylamine, the shape or geometry of the molecule is trigonal planar. Noted? Should I raise? Just one more question on same nitrogen family. On hydrolysis of NCl3, we get ammonium hydroxide and HOCl as the product. I'm not balancing the reaction. On hydrolysis of PCl3, we get H3PO4 and HCl. Right? So this is the data which is given in the question. The question is simply why. So I'm not asking that if this happens in NCl3, then what should happen in PCl3. It's a simple question. It's like this is given, you just have to explain it. Obviously, while drafting the multiple choice question, I'll draft it differently. That what is the byproduct of hydrolysis of NCl3? 4 options are given. What is the byproduct of hydrolysis of PCl3 and whatever. What is hydrolysis, first of all? Reaction with water is called hydrolysis. So definitely the two are reacting with water. Both have same geometry, both have same shape, very similar structure. So NCl3 is nitrogen having a lone pair on it and 3 chlorines are attached to it. Same goes for the phosphorus PCl3. So both have same geometry, same shape, but they're reacting differently with water. Question is why? Any clue? Nope. Okay. Let's see. So I'll explain it. Let's understand what happens with NCl3. So when I have NCl3, the nitrogen is bonded to 3 chlorine atoms and it has a lone pair on it. 3 chlorine atoms also have lone pair on it, but this nitrogen is capable of forming a hydrogen bond with H2. Right? And moreover, you can also say that because of the smaller size of nitrogen atom, the electron charge density on nitrogen atom will be higher than that of chlorine. right? So that's why it will be attracted more towards the hydrogen will be more attracted with the nitrogen than with the chlorine. Or I can say that if this bond breaks, which it happens, like I mean H2O partially breaks down into H plus and OH minus, which is called self-ionization of water. So the H plus will come to nitrogen, or I can say that this can get protonated. Right? Now if you have a H2O molecule in which oxygen has a lone pair of electron, and if it attacks a chlorine atom, why will it attack a chlorine atom? Because the chlorine is electron deficient here. Nitrogen and chlorine both have almost very similar electronegativity values. It is 3 and this is 3.2, quite close values. And since nitrogen has a positive charge on it, so its electronegativity will increase, and thereby this chlorine will be electron deficient. So oxygen will attack this chlorine, and thereby this will come out, which means what I'll have is HOHCl plus. So this is like a nucleophilic substitution kind of reaction. And what I'll have it is NHCl and Cl, lone pair. Obviously, oxygen with a positive charge will not be stable. It will remove NH plus and will form this HOCl. So in one step, what has happened is, if I just summarize the mechanism of the reaction, when I'm hydrolyzing NCl, the hydrogen got added to the nitrogen and OH got added with the chlorine, and this bond broke. Right? यहाँ पे hydrogen लग गया और यहाँ पर chlorine के साथ में OH लग गया. तो H2O को we can break down into H and OH, and we can say that this is how they have reacted, just to remember the reaction. We're not going into the mechanism every time. So we can quickly say one bond will be replaced like this. Similar thing will happen with other NCl bonds. So if I replace all the 3 bonds around nitrogen, what I'll get is ammonia. Got it? All the 3 chlorine will combine with OH will form HOCl, hypochlorous acid. Right? Ammonia in water form ammonium hydroxide. So these were the product. So even if you do not want to get into mechanism of it, you can simply remember what is happening here is that the hydrogen will combine with the nitrogen and OH will combine with the chlorine, and this bond will break down. And that's how it will be forming the ammonia, and thereby this. Why it happens? If you won't go into the depth of it. So this happens because the nitrogen has more electron charge density, will bind with the proton, and thereby will remove the OH minus from here, or you can say that this nitrogen will combine with hydrogen and H2O will combine with the chlorine. Because it will become electron deficient, it has vacant orbital. It will go and attack here. This NHCl2 will come out. This reaction will get repeated again and again. And then so those steps और हो जाएंगे. And after that, what you will get is ammonia and HOCl. So 3 moles of HOCl will be formed and 1 mole of ammonia will be formed through this reaction from 1 molecule of NCl3. Ammonia in water gets dissolved and reacts with it and form ammonium hydroxide. So that's what is the product. Got it? Now, in a similar fashion, the other reaction can also be explained, which was the reaction with PCl3. So on hydrolysis of PCl3, you get H3PO4 and HCl. So in PCl3, chlorine is more electronegative than phosphorus, so it will pull electron from the sigma bond, and this phosphorus will be electron deficient. Though it has a lone pair on it, but it also have some vacant d orbital, and it can accept a lone pair of electron. So this phosphorus has a vacant orbital and is electron deficient, so it can act as a Lewis acid. So this H2O from its oxygen will attack here, and the Cl will eventually come out and will get protonated. So I can say that OH will bind to the phosphorus and H will bind to the chlorine, and gradually it will be replacing OH, 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 OH and OH, and you can remember it as 3HCl. right? So too many OH would or definitely will not be stable. Obviously, this is not how it is happening, but this is how we can remember it. So I can remove H2O from it and can say there will be a oxy linkage that will be formed, right? So this is nothing but this is P double bond OH, OH and OH. This is nothing but H3PO4. You can also link the concept to the unavailability of d orbital on nitrogen atom, right? Because nitrogen did not have vacant d orbital, so oxygen could not attack on the nitrogen atom. So that's another added reason to it, and you can remember it this way. So PCl3, AS, HCl3 or any other trihalides of the nitrogen family except nitrogen reacts in this fashion, whereas nitrogen halides react in a different fashion altogether. So this is an important point which is usually asked in competitive exam in different ways. We should remember it, right? So now let's move on to the oxygen family. Should I erase it? So in oxygen family, we studied about various properties of the oxygen family: oxygen, sulfur, selenium, tellurium, and polonium. About their atomic number, about their atomic mass, their atomic radii, the size increases down the group, right? Which we know. The ionization enthalpy decreases down the group, which we know. The electronegativity decreases down the group, which we also know. The electron affinity decreases down the group. We also discussed that, in which there is a small exception here between sulfur and oxygen. So ideally it should have been oxygen, sulfur, selenium and tellurium and polonium. But there is a small change here to sulfur, oxygen, selenium, tellurium and polonium. Why does this happen? Because of interelectronic repulsion in the small 2p subshell, which does not happen that much in 3p subshell. So the same reason which happens in case of fluorine and chlorine, right? And we discussed about electron affinity and electron gain enthalpy also in the last lecture. This is about their property. Okay, and one more important thing which is across the period actually. Like, I mean, if I go from carbon, nitrogen, oxygen, fluorine, on going from left to right in a period, ionization enthalpy increases. But something happens between the two. I mean, ideally the order should be carbon, nitrogen, then oxygen, then fluorine. But the order that comes out to be carbon, nitrogen and then fluorine. Why? Because of the half-filled electronic configuration of the nitrogen. And the same behavior happens in case of other elements, like if I just compare. So for example, I have group 15 element, nitrogen, phosphorus, arsenic, antimony, bismuth, carbon, silicon, germanium, tin, lead, oxygen, sulfur, selenium, tellurium and polonium, fluorine, chlorine, bromine, iodine and acetylene. So on going from left to right in a period, the ionization enthalpy increases. So ideally the order should have been like this. But we know that there is an exception because of half-filled electronic configuration of nitrogen, which is more stable. This order changes. So the actual order becomes carbon, oxygen, nitrogen and then fluorine, right? Since the same case is happening here, because electronic configurations are similar in case of the elements of a group. So this is 3p3 and this is 3p4. Like this is 2p3, 2p4. This is 4p3, 4p4, 5p3, 5p4, 6p3, 6p4. So the order should also come out in the case of phosphorus and sulfur. The order should also come out in the case of arsenic and selenium. The order should also come out in the form of antimony and tellurium, and should also in the case of bismuth and polonium. But point to be remembered here is it does not happen here, which means I would just do it in red, which is changing, and the one which is not changing is like suppose in black. So these are half-filled electronic configurations and these are partially filled electronic configurations, and we know that NP3 is more stable than NP4. Removing an electron from half-filled electronic configuration will require more energy than from the partially filled electronic configuration. Moreover, on removing electron from NP4, it becomes NP3, which is again stable. So it is adding to some sort of stability. So definitely the energy required will be less in case of NP4. So this effect is prominent and reverses the trend in between nitrogen oxygen, between phosphorus and sulfur, between arsenic and selenium, but does not reverse the sign between antimony, tellurium and bismuth polonium. So why it does happen is because, like, see, here we are talking about difference in the stability of 2p3 and 2p4. Here we are talking about difference in the stability of 3p3 and 3p4. Here it is 4p3 and 4p4. Here it is 5p3 and 5p4. Here it is 6p3 and 6p4. Now what really happens when we go down the group, the size of the orbital increases and its energy changes, right? So so definitely 2p3 is more stable than 2p4, 3p3 is more stable than 3p4, and this is same happening down the group. But difference in their stability is not that high when we go down the group. Like for example, 2p3 is much more stable than 2p4. For example, if I just try and represent it like by number of these greater than sign, so 3p3 would be like probably like this. 4p3 and 4p4 will be like this. So this will keep on decreasing. So there is definitely a difference in stability, but because of increase in size, the difference in the stability of half filled and partially filled decreases. 6p3 is definitely more stable than 6p4, but difference in stability is not that high that it can reverse the trend. ये definitely एक difference है इनके बीच में, but इतना ज़्यादा difference नहीं है कि trend को पलट दे. But here the difference in their stability is that high that it can reverse the trend. So trend gets reversed in these three cases. So just remember that this is a very common case. This is not that common, like I mean in competitive exam this has been asked sometimes, but this has not been asked ever, and this has also not been asked ever, but can be asked. So you should remember it. Done? Should I erase it? Now, the next is molecular form of oxygen and sulfur. So oxygen exists in diatomic and triatomic molecular form. Both of them are gaseous at room temperature. This is called dioxygen and this is called ozone. In case of sulfur, sulfur exists primarily in the case form of S8, which is the crown shaped ring. So this is S8. Another is S6, which is in the chair form. So sulfur exists in monoclinic and rhombic form. This is also called alpha form and beta form. So rhombic sulfur is primarily S8, and it's a solid substance, pale yellowish color solid, which melts at around 114.5 degrees Celsius. Monoclinic is created by heating the rhombic sulfur, making a crust of it, drilling a hole into it, and then removing the liquid molten sulfur, and you'll find needle-shaped crystals at the bottom. So these needle-shaped crystals actually have the monoclinic structure. So these rhombic and monoclinic are the ones we studied in solid state. So we're talking about their three-dimensional arrangement. If you remember rhombic unit cell, monoclinic unit cell, right? So we just so they're different in crystalline form, and these are called allotropic forms. Sulfur also exists in the form of S6, which is chair form. It does not form the S2. It happens, it forms S2 only at higher temperatures, right? So the common question which comes here is that oxygen is forming O2 and O3 kind of molecules, whereas sulfur is preferring to form S6 or S8 kind of molecule. Why?
Small size.
No. Something will fit. So okay. So because of the p pi bonding, which is strong in case of oxygen and not strong in case of sulfur. So what is p pi bonding? So the atoms, same atoms which have p orbital, through which they can form p pi. So they can form pi bonds. It happens easily in case of oxygen, or I mean the elements which have smaller size, because if these p orbitals are small in size, they'll form stronger pi bonds. If these p orbitals are larger in size, they'll form weaker pi bonds. So this does not happen that frequently in case of elements of larger size. So they prefer to form single bonds instead of multiple bonds, which is the case in O2 or O3. The same thing happens between N2 and P4. In nitrogen, it can form triple bond, whereas in P4 it forms single bond and forms the P4 tetrahedral structure, right? Oxidation state of, or oxidation states of oxygen family. So in oxygen family, except oxygen, the oxidation shown by the members of the oxygen family ranges from -2 to +6. This is except oxygen. So it means when I'm talking about sulfur, selenium, tellurium, and polonium. Right? For oxygen, it is -2 to +2. It cannot expand its oxidation state beyond +2 because of the absence of the vacant d orbital and its highly electronegative nature. Right? In oxygen, from -2 to +2, I can divide it into various categories. So oxygen combines with most of the elements and form their respective oxides, in which oxygen is in -2 oxidation state. With some of the element, it combines in the form of peroxides, in which its oxidation state is -1. In some of the compound, it combines in the form of superoxides, where its oxidation state is -1/2. Right? These are the ones which is in the negative. 0 when it is in the pure elemental state, O2 or O3. When it will be +1 or maybe +2. So any element have the positive oxidation state, or occurred the positive oxidation state in any element when it combines with the element which is more electronegative than this element, right? So there is only one element which is more electronegative than oxygen, which is fluorine. So this happens when it combines with fluorine. So in O2F2, this is +1. In case of OF2, this is +2, right? So this happens with the oxidation states of the oxygen. So in most of the cases, it keeps this -2 as the oxidation state. In some compounds, -1. In very few compounds, it forms superoxide, so that's -0.5. 0, it's there in like it's a pure elemental form. There are like two limited compounds in which it forms +1 and +2. Right? There are some compounds also in which it can form +1 and +2 when it combined with, for example, hexafluoride fluoridoplatinum, like O2 plus PTF6 minus. So in which oxidation state of oxygen will be +1/2, right? So O2 plus, it's forming there. We'll talk about it. So oxide is O2 minus, peroxide is O2 2 minus, superoxide is O2 minus as an ion. Now let's talk about the other oxygen family members. Sulfur, selenium, tellurium and polonium, they can expand their oxidation state to +6. So +6 is the group oxidation state. Right? So definitely +4 will be the one which is oxidation state 2 unit lesser than the group oxidation state. So oxidation state which is 2 unit lesser than the group oxidation state. Stability of +4, stability increases, and stability of +6 decreases due to inert pair effect. बहुत बढ़िया. ठीक है? So which means that polonium will not prefer to have its compound in +6 oxidation state, but will prefer to have its compound in +4 or maybe in +2, right? So sulfur usually shows compound in +6. Selenium shows +6, but in very few compounds. Tellurium almost like no compound in which it shows +6, and polonium not at all. So even if we form the compound in +6 oxidation state, it quickly have tendency to come back to the +4 or +2 state, in which they will be getting reduced and thereby will be oxidizing the other substance. So if I form any compound of tellurium or polonium in +6 oxidation state, it will act as a powerful oxidizing agent. Good. Now, sulfur, selenium and tellurium, so they show -2 oxidation state, but in very few compounds. In most of the compounds, they show positive oxidation states. Like for example, if I talk about -2, this can be seen in case of sulfides, H2S for example, or for example CuS, copper sulfide, which is cupric sulfide precisely, in which S is present in the form of S2 minus, very similar to oxides. But these compounds not being that electronegative, so combined preferably with more electronegative elements like halogens and oxygen, and form compounds which are in +2, +4 and +6. So most common oxidation states of oxygen family is +2, +4 and +6, except oxygen. For oxygen, it is the most common oxidation state is -2. Like for example, if I talk about the popular compound of sulfur, sulfur dioxide SO2, it is present in +4, sulfur trioxide +6, sulfur hexafluoride SF6 +6, sulfuric acid, sulfur in +6, sulfurous acid +4. So the most common like oxidation states are in +4 and +6. In fact, +2 is there, but in some compounds. +1 is also there, but in very few compounds like S2Cl2, in which sulfur is in +1 oxidation state. So the range is there, which means that there are some or maybe very few compounds which are present in the oxidation state which are not listed here, but comes in this range. But definitely there will not be any compound which is in the which has oxidation state higher than +6 or lower than -2, right? Advantage of it is, for example, I have a compound of sulfur in +6 oxidation state, which is H2SO4. Now this compound can undergo a redox reaction. If it's reacting with some substance, for example H2O2, which can act as an oxidizing agent or as well as a reducing agent. Now sulfuric acid, so I just want to also understand, like in front of H2O2, does this H2SO4 have a choice or not? So we see that sulfur is in +6 oxidation state. If we want to oxidize this sulfur, I cannot increase its oxidation state because this is the highest value it can attain. It cannot attain any oxidation state higher than +6, which means it cannot be oxidized further. But it can get reduced, so its oxidation state can be decreased, so it can only function as a oxidizing agent. can only act as oxidizing agent. In fact, this is the reason, we'll talk about it. This is the reason why sulfuric acid can function as an oxidizing agent, not as a reducing agent. Similarly, H2S is used as a reducing agent in many reactions in metallurgy, or in inorganic chemistry as a whole. So in this case, sulfur is present in -2 oxidation state. Its oxidation state cannot be decreased further. It can only be increased. So this compound can only be oxidized if it's participating in a redox reaction. So if it can increase, so it will get oxidized, so it will function as a, so it can only act as. So this is the advantage of knowing the range. So what is the range of oxidation state in nitrogen family? What is the range of oxidation state in nitrogen family? Very similar kind of range. What is the range?
-3 to +5.
-3 to +5. Perfect. So the oxidation state, range of oxidation state in nitrogen family members is -3 to +5. So they cannot have any compound in which their element, the element of the nitrogen family has oxidation state higher than +5 or lower than -3. Any element, any compound of them in which the element is present in higher oxidation state, like +5, will be functioning as an oxidizing agent. For example, HNO3. In nitric acid, nitrogen is present in +5 oxidation state. It's a strongly electronegative element and present in very high oxidation state, and cannot function as a reducing agent at all, can only function as an oxidizing agent, and it does function as a powerful oxidizing agent, right? Similarly, H3PO4 can function as a oxidizing agent, not reducing, +5 phosphorus, right? Can you give me an example in which any compound of nitrogen family can function only as a reducing agent? No. A compound of nitrogen family in which that compound can only function as a reducing agent and not at all as an oxidizing agent. It should be the compound. No, you should see. You're not understanding the logic behind it. See, if I have range of compounds, for example, NH3NO, or maybe NH3N2NO, NO2, for example, or HNO3, right? So if I see these range of compounds, or maybe I'll take one more in between, let's suppose N3H. Let's just quickly write down the oxidation states of all these, of nitrogen in all these compounds. It will be -3 here. It will be -1/3 here. It will be 0, +2, +4, and +5. What is the range of oxidation state of nitrogen? -3 to +5. So it cannot have any oxidation state higher than +5. It cannot have any oxidation state lower than -3. Whenever oxidation state increases, oxidation happens. Whenever oxidation state decreases, reduction happens. The substance which is undergoing oxidation is functioning as a reducing agent. The substance undergoing reduction is functioning as an oxidizing agent. So nitrogen in +5 cannot increase its oxidation state. It will only have tendency to reduce its oxidation state to lower value. If it has only +5 as the oxidation state, which is for example there, which is the highest value, so which will only decrease. When it will decrease, it will be getting reduced and it will be functioning as a oxidizing agent. Since it cannot increase, it cannot get oxidized, cannot function as a reducing agent. So I can conclude that this compound, if at all it is undergoing a redox reaction, this will only play the role of oxidizing agent or oxidant, right? Similarly, this compound of nitrogen, which is present in its lowest oxidation state, cannot decrease its oxidation state, so cannot get reduced and cannot function as a oxidizing agent, but can increase its oxidation state. If it can increase its oxidation state, it will get oxidized and can only function as reducing agent or reductant. Now if I extend this logic to other compounds of nitrogen family. So these compounds have oxidation state which can either decrease or increase depending upon the situation, reaction conditions and various other circumstances. So I can say that they can be reductant or oxidant. I cannot comment because that will purely depend upon with whom they are reacting, what is the situation, temperature conditions, pressure conditions and various other factors. But yes, looking at their oxidation state, it can increase, it can decrease, they can show increase or decrease, or they can function as a reducing agent as well as a oxidizing agent. Point 1. Point 2, similarly, because these elements are present in the interim values of range of oxidation states. So these elements can disproportionate. What is this disproportionation? When same element gets oxidized as well as reduced. So these elements have the option, or I would say like possibility of reducing their oxidation state as well as increasing, because this element cannot disproportionate. This substance cannot disproportionate because the element is already present in its higher oxidation state. It can get only reduced, it cannot get oxidized. So this will not disproportionate, this will never disproportionate, but the element in between can disproportionate. The same example which we took, if you remember, H3PO3. So phosphorus, in H3PO3, phosphorus is present in +3 oxidation state. It goes to +5 and it goes to -3. Right? Point 1. Point 2, which you should also remember in this case, is that you should not take it as a misconception that like an phosphorus went from +3 to +5 and -3. In phosphine it is -3 and in H3PO4 it is +5. This is the example which we took. Remember, H3PO3 on heating converts to H3PO4 and PH3. So in this case, phosphorus is present in -3 oxidation state. In this case, it is +5. In this case, it is +3. So you should not take it as a misconception that whenever an element disproportionate, it goes to extreme oxidation states. This is wrong. One will increase, one will decrease, but that increase may not be the highest or the lowest one. In this case, it is happening in such a way, but it may not be. It can be just one value up, one value down. Got it? There's a doubt which is about the oxidation state of the hypohalous acid, which is specifically hypofluorous acid, and about the acidic strength of nitrous and nitric acid. I'll take up this doubt in halogens, because this is something which we'll definitely cover. So I'm not discussing it now because it'll just break the flow. Should I erase it? So this is about the oxidation state which you should keep in mind in general. I'll be discussing again in case of halogens. Now if I talk about oxides of oxygen family, so they primarily show EO2 and EO3 kind of oxides except oxygen. So like for example, you see SO2 and SO3 as the oxides, SeO2 and SeO3 as the oxides. The oxides of sulfur, SO2 and SO3, are gases at room temperature. Whereas oxides of SeO2 and SeO3, they are solid at room temperature and they do not exist in the monomer form or monomeric form, I would say, in the form of single units. Like for example, SO2 exists in the form of monomeric units. Like single SO2 you can there might be, because there's a lot of smog these days. So there might be one, or not just one, but many SO2 molecules moving around me, right? And similarly in case of SO3, but in case of SeO3 or SeO2, it is formed in the polymeric state, maybe dimeric, trimeric, and so on. So like for example, SeO3 is found in tetrameric state. So it will be Se4O12. This is tetramer. Mer means unit and tetra is 4. So monomer means 1 unit, polymer means many units. So tetramer means 4 units. So how they're combined with each other? So just draw a rhombus, or I would say a square, in which 4 selenium are there bonded through oxygen, and every selenium has 2 oxo linkage, double bond O, double bond O. This is your Se4O12. So what kind of question can be asked from it? A simple integer type question. Number of SO, S bonds, number of oxo linkages, or number of, maybe, so it could be just like, random question, because you do not know how they're bonded. What is the number of Se bonds in it? 0. So that's also an integer. Right. So important thing in the oxides of the oxygen family is that they are acidic in nature. Especially if I talk about the SO2 and SO3, both of them are significantly acidic gas. That is why these days you're feeling burning or irritation in your eyes, because the moisture around your eyes can react with SO2, can form sulfurous acid and sulfuric acid, which will start reacting with other molecules present on the outer layer of your eye. Not going into the biology. Got it? And the similar thing happens when you cut onion. So it has sulfur compounds, which forms SO2 or SO3 that reacts with your eye moisture and so on. Should I erase it? So these are acidic gases. So let's just talk about them. How can we prepare these oxides, and what are the properties? So SO2 sulfur dioxide, it has sp2 hybridization with a lone pair on it. It has a bent shape, and it has 2 pi bonds. One of the pi bond is formed by 2p and 3p, and another pi bond is formed by 2p and 3d. So oxygen definitely does not have a 3d or 3p. So this 2p actually belongs to oxygen. So one of the pi bond is formed by 2p orbital of oxygen and 3p orbital of sulfur. One of the pi bond is formed by 2p orbital of oxygen and on 3d orbital of sulfur. How can you check that? Sulfur has electronic configuration 3s2 3p4. So in valence shell 3s2 3p4 and a vacant 3d subshell. Right. Now what really happens in this case, one of this electron gets excited and moves to 3d. Sulfur utilizes these 3 orbitals to form bond, and form sp2 hybridization. So one of the sp2 hybrid orbital carries the lone pair, and the other 2 sp2 hybrid orbitals forms a sigma bond. So sigma bonds are formed by sp2 hybrid orbital of sulfur, these 2 sigma bonds. So sulfur has 2 half-filled orbitals. One is in 3p and another is in 3d. And oxygen also has one such similar half-filled orbital through which they can form the pi bond. So oxygen has one 2pz, for example, and sulfur has one 3pz. The two can form pi bond. Oxygen has, for example, a 2pz, and for example, sulfur has a, which one? Maybe 3dyz or 3dz2 or something else. So let's not get into that, which one is that, because that will complicate the matter here right now. So this will be the one of the 3d orbital through which it will overlap and form the pi bond. Got it? Should I erase? Okay. So this is about the structure of SO2. So SO2 can be formed, it can be produced by roasting. So this is another technique which we use in metallurgy. Whenever we have sulfur ores or sulfide ores, I would say, so sulfides or persulfide, on heating strongly them in presence of oxygen, they form SO2. Like for example, Cu2s on heating with O2 will form SO2. It is also a byproduct in many of the reactions. What else will be formed here? Fe2O3, and it will be CuO. Right. So this is a typical reaction which we use in metallurgy, and we call this process roasting. So this is one of the method of producing SO2. Yeah, I think this is it. So SO2 is acidic in nature. Its acidic nature can be observed by its reaction with water to form what? H2SO3 called sulfurous acid. So it reacts with water to form sulfurous acid. So SO2 can show a lot of reactions in which it is acting as a acid. In which reaction? Those reactions in which the reactions are happening in aqueous medium. Those reactions which are not happening in aqueous medium, still it can act as a acid, but not really the areneous acid like sulfurous acid, but as a acidic oxide. Like for example, I have calcium oxide, which is a basic oxide, and it is reacting with sulfur dioxide gas. So it will form CaSO3, calcium sulfite. Right? The basic oxide, the acidic oxide, and the salt. So on heating strongly, calcium oxide in the atmosphere of SO2, the two can react and form this. Right? Since SO2 being acidic gas, in cases of eudiometry, what is eudiometry? The study or actually quantitative measurements of the gaseous reactions. Like I mean, for example, you might have seen a lot of questions around it. Like for example, you have taken two gases, which are like for example SO2 and O2, and they were taken in some volumes. And a spark was produced, and you observed a contraction of 17 ml. The left volume, the left mixture of gases was passed through some solution. Then volume contraction was this much, or expansion was this much. This is how you observe the volume changes. So if I have in such eudiometry, I'm just relating it to one property here because I'll just tell you why. So SO2 gas, being an acidic gas, can be dissolved in a solution which is alkaline. So if I'll pass a mixture of gases which contains one of the gases SO2 and none of the other gas as acidic gas, or maybe if there are others, but definitely SO2 when being passed through the alkaline solution, this is being acidic gas. If I'll pass it through the alkaline solution, this will start reacting with water and will form H2SO3. The H2SO3 and KOH will form. So if the two are keep on reacting, so because of the less reversibility of the reaction, or like I mean I would say more irreversibility of the reaction will keep on going in the forward direction. So I can say that SO2 is highly soluble in alkaline solutions, or can be dissolved in alkaline solution. This is how we can perceive it. Should I erase it? Another important property of SO2 is its bleaching action. So SO2 on reaction with water can produce some quantity of H2SO4 and nascent hydrogen. So because of this nascent hydrogen, it can function as a reducing agent. See, in sulfur, in SO2, sulfur is present in +4 oxidation state. So it can either increase or decrease. If it increases, it will function as a reducing agent. If it decreases, it will function as an oxidizing agent. So SO2 can act as oxidizing as well as reducing agent. So in many of the reactions of SO2, you'll observe it as an oxidizing agent. In some of the reactions of SO2, you'll see it as a reducing agent. So now, for example, I'm talking about the bleaching action of SO2. What happens in bleaching action? The colored matter is converted to colorless matter. Okay, this is happen in case of bleaching in general. Forget about SO2 right now. So what really happens in bleaching? Bleaching is actually removing the color of the colored matter. So if, for example, if I have a dye or any substance, for example, the very basic example is, let's suppose, the cotton. So the cotton fiber which we obtain from plants are not pure white. It's off-white in color. But if I want a pure white shirt, or maybe I want a different color shirt which we wear these days, or not just shirt but any other material. I'm obsessed with shirts probably. So so the colored matter which is present in the cotton is removed by the bleaching action. Right? People